Hi, this is Dr. Frank Zhang. Thank you for your interest in Rice State University. I would like to take this opportunity to introduce myself, my background, courses I teach, and my research work. I obtained my PhD in electrical engineering from University of Cincinnati in 2002. Then I joined Intelligent Automation Incorporated in Rockville, Maryland as a senior research engineer. In 2005, I became a senior researcher at General Motors R&D Center in Warren, Michigan. I joined Wright State University in 2007 as an assistant professor. Currently, I'm a professor of electrical engineering. I'm in the area of control and robotics. Control engineering is the engineering discipline that focuses on mathematical modeling of systems of a diverse nature, analyzing their dynamic behaviors, and designing a controller that will cause the system to behave in a desired manner. Robotics is the science and technology of robots and their design, manufacture, and applications. Recent rapid developments in artificial intelligence is revolutionizing the field of control robotics. Some good examples include autonomous vehicles with self-driving capability, unmanned air vehicles or UAVs with various potential military and civilian applications, including security patrol, search and rescue, aerial photography, power line inspection, package delivery, etc. I have supervised 3 PhD students and 12 master students. I have over 90 research publications in the area of intelligent autonomous systems. I'm a member of the IFSC Steering Committee on Fault Detection, Supervision, and Safety for Technical Processes. In the past, I also served as an associate editor for the Journal of IEEE Transactions on Control System Technology. These are the courses I have taught at Rice State University. At undergraduate level, I have taught Linear System 1, Continuous Control Systems, Digital Control Systems, Intro to Intelligent Control Systems, and Autonomous UAV Flight Control. At the graduate level, I have taught Modern Control 1, Autonomous Unmanned Systems, Adaptive Control, and Intelligent Control Systems. Next, let me give you some examples of courses I teach. Let's start with EE4130, Continuous Control Systems. The figure on the top left shows the structure of a typical feedback control system. The objective of the controller is to have the plant's actual output follow the desired command. For instance, in the case of cruise control, the objective is to have the vehicle speed follow the desired set point, even in the presence of disturbances such as wind and variations of road conditions. The figure on the top right shows the typical system response to a step command, which consists of 2 parts, the steady-state response and the transient response. The objective of control design is to ensure the system response meets the specifications in terms of steady-state error and transient response, such as response speed, maximum overshoot, and settling time, etc. More specifically, the topics covered in this course include chance function models, stability analysis, steady-state error, transient response analysis. These topics pave the way for the most exciting an interesting part of the course, that is Pid Controller Design. We will present 3 approaches, including second-order prototype system method, root locus method, and the body plot method. The strength of our curriculum is the seamless integration of lectures with labs. For instance, for this course, in the weekly lab, students use the cube servo system from Conza to implement and practice the control concept and theory taught in lectures. With the Quark real-time control software, students can develop the control solutions using MATLAB Simulink and easily validate their algorithms with the hardware system in real time. With the development of the digital processor technology, digital control, where the control algorithms are implemented on a microcontroller, has been widely applied in industry. Digital control systems are flexible, inexpensive, scalable, and adaptable. As shown in the top right figure, the interface at the input of the computer is an analog to digital converter, which converts sensor signals into a form that can be readily processed by the computer. At the computer output, a digital to analog converter is required to convert the binary signals of the computer into a form necessary to drive the plant. Since digital control systems are discrete time systems, the Laplace transform-based design and analysis methods covered in EE 4130 are no longer applicable. This course is the second in a 2-course control series. The course introduces feedback computer controller systems, the components of digital control systems, analysis of system stability, and time response characteristics. Various discrete time controllers are designed, including digital PID, phase lead, phase lag, and state feedback controllers. In the weekly lab, students design, implement, and evaluate their controllers for an educational spring mass damper system. Students also get extensive hands-on experience with the D-Space rapid controlled prototyping system, which is widely used in industry. In response to the emerging technology of autonomous systems, recently we have developed 2 new courses, EE 4600 Autonomous UAV Flight Control at the undergraduate level and EE 7600 Autonomous Unmanned Systems at the graduate level. In EE 4600, we take our students through all important steps of flight control system design for cold rotor UAVs. The first step in developing navigation guidance and control strategies for UAVs is to develop dynamic models describing the vehicle's motion. Related topics of coordinate frames and transformation, equations of motion, and system identification techniques are first covered in this course. The nonlinear state space model is linearized to create transfer function models appropriate for control design. Then, the successive loop closure method and PID controllers are presented to create a fully autonomous flight control system that controls the vehicle's position and attitude during all phases of flight. Students carry out weekly lab designs in our UAV lab equipped with first-class experimental facilities, which culminates with real-time flight tests of their autopilot systems towards the end of the semester.
At the Department of Electrical Engineering, Wright State University, we emphasize the seamless and thoughtful integration of lecture with lab sections. We believe in learning through practice and innovation. Thank you again for watching the video. If you have any questions, please feel free to contact me. I hope to see you in the near future at Wright State.